MaskFlownet, asymmetric feature matching with learnable occlusion mask. Optical flow estimation is to measure the pixel-wise correspondence between the source image and the target image. It is a core problem in computer vision and a fundamental building block of many real-world applications. Recently, PWC-Net and LightFlowNet propose a compact design of convolutional neural network-based architecture with feature pyramid, warping operation, and cost volume. Feature warping effectively resolves the long-range matching problem between feature maps for the cost-volume computation. However, feature warping introduces ambiguity in the presence of occlusions. As shown in this figure, the warped image can be even doubled at the occluded areas. It remains unclear that whether the source image would be mismatched to such areas, yet it raises another natural question. Are they distinguishable without being supervised of occlusions? We answer this positively by showing that the network can indeed learn to mask such area without any explicit supervision. We first review the plain feature matching module as used in PWC-Net, consisting of the warping operation and the correlation layer. Here, phi denotes the predicted flow field. Our learnable occlusion mask, denoted by theta, filters useless information immediately after the warping operation, and there is an additive trade-off term, denoted by mu, which facilitates the learning of occlusions. We further propose the asymmetric occlusion-aware feature matching module, which introduces an extra deformable convolutional layer prior to the warping operation. This simple asymmetric design leads to considerable performance gains. At each level of the network, the learnable occlusion mask is generated through the sigmoid activation from the previous level, upsampled, and then fed into the asymmetric occlusion-aware feature matching module. We demonstrate how the proposed asymmetric occlusion-aware feature matching module contributes to the overall performance using a two-stage architecture, MaskFlownet. The first stage, named MaskFlownet S, generally inherits the network architecture from PWC-Net, but replaces the plain feature matching modules by the proposed asymmetric occlusion-aware feature matching modules. In the second stage, the learned occlusion mask is concatenated with the warp image and fed into the occlusion-aware feature pyramid, which, together with the original plain feature pyramids, form the dual pyramid structure. At the time of submission, MaskFlownet surpasses all published optical flow methods on MPI Cinto on both clean and final pass, KT 2020 and 2050 benchmarks, while using only two frame inputs with no additional assumption. Now let's have a look at how each component works. This figure qualitatively demonstrates that the learned occlusion mask matches to the inverse of ground truth occlusion fairly well, even if it is learned without any explicit supervision. In the asymmetric occlusion-aware feature matching module, those are feature maps prior to the cost volume. Comparing the source features with the target features, we can see that the network does learn very different feature representations. Also, the learnable occlusion mask fails to achieve a clear estimation at first, but with the help of the trade-off term, large occlusions are successfully learned. As for the occlusion-aware feature pyramid, comparing the feature with and without the learned occlusion mask, we can see that it draws significant effect on smoothing the feature map at the occluded areas. As a conclusion, we propose the asymmetric occlusion-aware feature matching module, which incorporates a learnable occlusion mask without any explicit supervision, and can be easily integrated into end-to-end network architectures while introducing negligible computational cost. We expect it to open a new perspective on dealing with occlusion and to be an initiative and effective component for optic flow and many other applications. For more details, please go and check our GitHub repository.